Alright guys, so we're talking about what quadratics can be used for. Quadratics are a really useful type of mathematical function. One thing they're used for is for solving projectiles. Anybody in here that's in physics? Anybody here in physics? A lot of this will look probably familiar, and if it doesn't yet, it will. So this is kind of related to physics stuff. So we're going to talk about these things called projectiles. So what is a projectile? Basically, a projectile is anything that's under the influence of gravity alone. So, you know, whether you are just dropping an object that's under the influence of gravity, or if you throw something straight up in the air and it comes back down, or if you throw something a certain distance, all of those are considered to be projectiles because the point is once it leaves your hand, it's under the influence of gravity. And gravity actually has a quadratic effect on the object. And you can kind of tell that from the shape, especially with the last one over there. It follows the path of a parabola, right? All right. I don't think I wrote this slide out for you, so you guys might want to copy this down somewhere. Give you a minute. So this is quadratic. Notice that the input variable here is time. Okay, so we use t for time. And the h represents height. And I think it's fair to say we're always going to be doing this in seconds. So this is the height after t seconds. Okay, it's always going to be in seconds. In science, a lot of times when you have a variable with a little zero at the foot of it, that's called an initial condition or a starting amount. So what this represents is the starting height. And what the v represents here is the starting velocity. We might want to put here also in parentheses ft for feet, because the way that I'm giving you this formula right now, everything's in feet and seconds. The formula can change if you want to do like meters per second or something like that, but I think we'll just stick with feet per second. But there's that. You don't need to write this, but this number is not arbitrary. What it is that the Earth, because of its size, it has a certain pull on things, right? And you guys know, like when you're on the moon, for instance, it's smaller, and so it doesn't pull on things as much, and so things are kind of a little bit more floaty on the moon, right? Well, because of the size of the Earth, it pulls objects towards it, and that's what causes things to fall. And the rate at which that happens, the acceleration of that is 32 feet per second per second. And so what that means is after 1 second, it should be falling at a speed of 32 feet per second. After 2 seconds, it would be 64 feet per second. So every second, the speed increases by 32 feet per second. That's not considering other factors like wind or wind resistance. It's just the raw rate at which Earth pulls things towards it. Okay. Now, I said 32, not 16, but the 16 is basically, it comes from the math that they did to get this formula. In the process, you end up dividing it in half. So that's what that number is. So if I were to change this formula to like meters per second, this number would change because this is in feet per second, okay? Anyway, so that's our projectile. So basically this is a formula where if you were to plug in a time, it should be able to tell you how high up the object is at any given time. Okay, that's what it's for. But you have to know a couple things for that to happen. You have to know the starting speed and you have to know the starting height in order for that to work. If an object is launched from the ground level, then what's my starting height? 0. So let's put that. So if they won't say it equals 0 in the word problems, but if you ever see the word problem saying the starting height will start on the ground, you can assume that h sub 0 is 0. Now, velocity is speed. Basically, it tells you how fast something's going, but it also has direction associated with it. So if you throw something up in the air, we will call that a positive velocity. If you throw something downwards, that would be a negative velocity. And if you just let it go, then the starting velocity is 0. It starts at no speed and gravity starts pulling on it right away. But it does start at a speed of 0. So if an object is just dropped rather than thrown, then the starting velocity is 0. Now, I don't remember if we're going to encounter too much of this today, but we should probably write it. So let's write the following things as well. If an object is launched upwards, then the starting velocity is positive. And if an object is launched downwards, the starting velocity is negative. I think every problem we're going to do today is just a positive velocity. But just in case. So there it is. So I'll let you guys copy that for a sec. And then we'll get down to business. What we're going to do with this formula today is we're going to do a couple things. First of all, we're going to have a word problem, and you're going to use that formula to write an equation, okay? And that equation is a quadratic equation. So we're going to use the stuff that we learned to solve some stuff about this. First of all, you should be able to find out what the maximum height is. That's just the vertex, isn't it? And we learned how to find the vertex, right? So we got that. We can also find how long it takes for it to land on the ground. Not immediately obvious right now, but what that's going to be is that's basically the roots, is what that will be, or the x-intercepts, which we've also learned how to do. So here we go. I tried to make these as realistic as I could, but you know, probably not perfect. A bullet is fired straight up into the air from an initial height of 6 feet with an initial velocity of 900 feet per second. Okay, so our first thing that we want to do here is we want to write our equation that models this. So here we go. It's going to be h of t, right, equals the negative 16 will always be there, t squared. Now we're going to put our velocity in there. What's my velocity? My starting velocity.
So no matter what the question is it going to be the same?
Two numbers will change. And I'll show you those two numbers in just a second. Well, actually, the first one is going to be the next number I write, because the next number is the v with the little 0 next to it.
Yeah, but h of t equals negative 16.
That will always be there. Yep. Because the reason for that is because on Earth, gravity never changes. So it's always going to be negative 16 feet per second per second. So what comes next is our initial velocity. What's our starting velocity? It's 900. Now, is it a positive velocity? It's positive because it shot up in the air, right? Not down, but up. So we're going to say it's plus 900, and then there's a t next to it. And then after that comes our starting height. What's my starting height? 6 feet. Now, when you're talking about events that are as extreme as a bullet, the accuracy of your equation could suffer, right? Because air resistance and stuff like that can get in the way and really mess it up. So this won't be a perfect model, but you know, if we ignore those other things, this is kind of what would happen. But there's your equation basically. So what we have now is I've got a formula where if I were to plug in any t value, like let's say 3 seconds, if I were to plug in 3 for t, the output would tell me how high up the bullet is at that time. Okay? Can I erase? Now, we want to draw a picture of it. They're pretty much always going to look the same. The x-axis is going to be time. Okay? How do I know that? Because it's the variable in parentheses, and we learned in chapter 2, the one in parentheses is the input, and input goes on the horizontal axis, right? This is going to represent height. So I want you guys to understand something. This is not distance, okay? Although, you know, when we think of throwing something up in the air, it does travel a path like that, but we're not really looking at, we don't care about horizontal distance at all here. All we care about is time and height. So we don't know anything about horizontal distance here. All right, and besides, it says it fired it straight up in the air anyway, so there shouldn't be any horizontal distance. Okay, so there's our picture. How long does it take the bullet to reach its maximum height? So what that means is find the vertex. Okay, so how do we find the vertex? Well, first of all, this is in standard form, right? And yesterday we talked about how to find the vertex in standard form, right? The first thing you do is negative b over 2a, right? So my b is what in this case? 900, and my a is negative 16, right? I don't have a calculator, so but I think I might actually. Let me see. There's one. So I'm going to go ahead and work this out. The bottom's going to be negative 32. So I'm going to work it out just so I can see it. There it is. Okay. I do better with numbers I see than here. So 28.125. Now what would I do if I want to find my k? You get to plug it in. So it's negative 16 times 28.125 squared plus 900 times 28.125 plus 6. Okay? Let's go ahead and calculate that out. I'm going to use a different calculator, but you guys might want to try it as well. These graphing calculators are kind of nice. I think some of your cell phones even do this. You can just type the whole equation right in. So that's what I'm going to do. Negative 16, 28.125 squared plus 900 times 28.125 plus 6. So I just type it all in. I don't have to do it piece by piece. I end up with 12,662.25. Okay, so let's label that on our graph. That's kind of helpful to actually see that number on our graph. So we haven't answered the question yet exactly, because What's the question asking us to find? It asks, yeah, it's asking us how long does it take to reach its maximum height. So do they want to know a time value or a height value? They want to know a time value. So what's the answer? That's right. So this is the horizontal number, right? Time. So that's your time, and this is the height. So that's the time it takes to reach its maximum height, and that is the maximum height. Okay, so for part B, we're going to say t equals 28.125, and let's go ahead and give it some units. That's 28.125 what? Seconds. And once again, this is assuming there's no air resistance or weird stuff like that. Actually, it's not weird, it's normal, but we're just ignoring it. All right. Can I erase stuff? I think the next one says, what is the maximum height, right?
Yeah.
Okay.
The H and K, we don't have to do the K, or do we stop?
No, we did the K, and that's important because that's actually the answer to this one. The question now is, what is the maximum height? That's the output variable, which is the height, and so that's going to be 2662.25, and that's 12,662.25 what? Feet. I don't think that this is exactly accurate. I've looked up before, like, what's the height that a bullet actually reaches, and I forget. It's not that high. That's almost 2 miles, and the reason for that is, once again, air resistance. It slows it down and messes with it. So, but that's okay. We're ignoring that. All right. Next question. How long does it take to land on the ground? That's our next question. Well, when an object is on the ground, what's the height? 0. Now, there's 2 times, maybe, when the height is 0, right? But the one we care about is the one over here, correct? Okay, so here's my formula, right? We have h of t equals negative 16 t squared plus 900 t, what is it, plus 6? What equals 0? H equals 0, right? Where does that 0 go? Goes right there. We're going to set the equation equal to 0. In other words, what value of t will give me a height of 0? And that will tell you how to find when it lands on the ground. So the answer to this question is find the what? Roots. And how do you do that? Huh?
Use the quadratic.
Yeah. Use the quadratic formula. So, if you want to find out the maximum height, you do the negative b over 2a thing, right? If you want to find when it lands on the ground, use the quadratic formula. All right. So let's go ahead and do that. And once again, this is a calculator question. I mean, it's okay, so B is 900, C is 6, and A is negative 16. I got them backwards. Yeah, it doesn't matter, but it's okay. Just to be consistent, I'll write it correctly so people aren't confused. There we go. And we get to do a lot of calculator work here, so let's do it. Okay. So what is 900 to the second power? $810,000. This is going to become plus because of the double negatives. So we have 4 times 16 times 6, and that's 384. Bottom's going to be negative 32. Okay, now this is something that we haven't done yet, so I'm going to wait for a second in case you guys need to catch up, but we're going to do something a little bit differently here. Up till now, we've either had really nice numbers over there, or we just broke them down. I'm not going to expect you guys to break that down, it's a waste of time. And besides, we want just a normal number we can look at, not some weird thing with square roots in it. So we're just going to use our calculators, okay? So let's do the square root of 810,384. And we're going to have to round it. It's not going to be a perfect answer. So it says 900. Let's go ahead and go out to at least the third decimal place. So 900.213. Now at this point, something else that might be a little bit different is we're going to actually write two separate equations. We're going to write one where it's plus and one where it's minus, and we're going to calculate both. So we have Madison, you won't be so bored if you take notes with us. At least it'll help a little bit, and then you'll have something to look at whenever it's your turn to do the problem. Come back to reality, my dear. All right, so we're going to go ahead and add these together. That's going to end up being 0.213 over negative 32. And that's going to be some very tiny number. Let's see. Oops. Negative 32. So we end up with negative 0.007. And remember, that's seconds. Now, is there such a thing as negative time? No. We'll talk about why we're not using that one in a second. But let's come over here. Let's do this one now. I don't want to use this calculator. $56.257. Which one of these do you think represents best? The second one, right? Now there's two ways you can know that. First of all, there's no such thing as negative time. Also, that's a really small number. But then when you come back to our problem, remember how we said it was going to be the one, that, not the first point, but the second point, where it actually lands on the ground that we care about. So, there you have it.
Since the vertex lies in between both roots, can't we just technically just multiply the part of the vertex times 2. Just get
Not exactly. That's a good question. I like your question. So Nick's question was this. He's remembering that the vertex is right in the middle of the roots, right? So can't we just double the time of the vertex? It could be, and if you did this, you'd be really close. Now here's why not. Because the quadratic actually doesn't start at 0. It starts at 6. Remember, it started at a height of 6. So that's why the time was a little bit behind that with a negative number. So you'd be off like in the thousands. Not a big deal, right? Now, but what if you have a problem where like a basketball? Well, now 6 feet makes a huge difference. So you want to just kind of know that. But what you can do and what will work is what you could start by finding the roots first. Then you could find the distance between, cut it in half, and that'll find your vertex. That'll always work. But yeah, working the other way could cause some problems with the projectile problems. But good question. All right. So the rest of the block, I'm going to let you guys work on this. This is yours. Just get to practice a little bit. I don't think we have anything else after that. So we just have one big problem. So go ahead and see what you guys can do.